from Professor Remo Ruffini. After his degree in 1966, he was postdoctoral fellow at the Mainz Academy of Science, working with Pascual Jordan in Germany. Then he was a member of the Institute for Advanced Studies in Princeton, and later became instructor and assistant professor at Princeton University. In 1975, he was visiting a professor at the University of Kyoto, Japan, and of Western Australia in Perth. In the years 1975 to 78, he cooperated with NASA, being member of the task force on the scientific use of the space stations. In 1976, he became professor of theoretical physics at the University of Catania. And in 1978, he was appointed professor at the University La Sapienza in Rome. In 1985, he was elected president of the International Center for Relativistic Astrophysics. And in 1984, he was co-founder with Abdul Salam of the Marcel Grossman meetings. In 1987, he became co-chairman of the Italian-Korean meetings on relativistic astrophysics. In the years 1989 to 93, he was president of the scientific committee of the Italian Space Agency. He is editor of a variety of scientific journals. He is married to Ana Imponente and has a son, Jacopo. His theoretical works led to the concept of boson stars. His classical article with John Wheeler popularized the astrophysical concept of black holes. With Demetrius Christodoulou, he has given a formula for the Kerr-Newman black hole endowed of charge, mass, and angular momentum. His theoretical work led to the identification of the first black holes in the Milky Way. Together with his student, Rhodis, he established the absolute upper limit of the mass of the neutron stars, and with his students, Robert Liege, he used such an upper limit for fixing the paradigm which enabled the identifications of the first black hole in the Milky Way galaxy, Cygnus X1, using the splendid data of the UNRU satellite by Riccardo Giacconi and his group. For these works, Ruffini won the Cressy Morrison Award of the New York Academy of Science in 1972. With his students Calcetti, Javalisco, Song, and Taraglio, he developed the role of fractal structures in cosmology. Together with his collaborator, Damour, he suggested the applicability of the Heisenberg-Euler-Schwinger process of part creations in black hole physics and identified the diodosphere with this process take place. Gamma ray burst seems to give to the observational evidence of such part creation process in astrophysics prior to the observation of such phenomenon in Earth-based experiments and represented the first evidence of the extraction process of uh, black holes. Recently, he published the complete explanation of the gamma ray burst together with Roy Kerr. Then today, he will talk
a new look at Cygnus X1 following the comprehension of GRBs.
Okay.
Hello?
Please begin.
Can I start?
Yes.
Well, first of all, I would like to thank everyone for this great opportunity to be back at the Colegio Nacional in Mexico City. And this new Leopold García-Colín Mexican meeting on mathematical and experimental physics. Last time I was there giving a talk, I was working still very hard to the comprehension of GRBs. And this effort, which lasted 50 years, has been really accomplished only a few days ago, on October 1st this year, when our comprehensive article was published with, after some 20 or 30 other publications previous in APJ in 1st October. I would like to, but what is very interesting is that after this comprehension we have reached, everything is different. And we have a new understanding. And especially in my last lecture in Colegio Nacional, I received a question by somebody who was coming from an observatory in Mexico and working also in United States. And he asked me, okay, you understand the GRBs, but how do you explain Cygnus X1? Well, this meeting, this lecture is dedicated especially to him, because I want to show how all the previous work we have done can now be essential for a new understanding of the physics and astrophysics of Cygnus X1. I have the answer. But there are still revolutions coming, even bigger, which go back to the understanding which I will present in a few weeks in Hong Kong, that the Crab Nebula is very likely was not just a supernova, but was also a GRB. But let's go bit by bit. The Crab Nebula has been the most important and fundamental ever observation of man in the universe. It was observed by Chinese in 1054. Everybody knows the history of the Crab Nebula, how the detection improved, and this picture I show is one of the latest images of the crab, still today, after so many years, to be continuously expanding in 250 kilometers per second. And of course, the greatest discovery in the Crab Nebula happens in 1050, after the observation in 1054, happened in 1968, with Tony Hewish and Jocelyn Bell discovered in the Crab Nebula pulsar, also the Crab Nebula pulsar, pulsating with, still today with 33 milliseconds. At this year, I was just young, as we have called a moment ago, as a young postdoc and coming to Princeton, working with John Wheeler. And it was precisely in 1971 that with John Wheeler, we introduced the concept of the black hole as a new object based on the Kerr metric, which had been obtained by Kerr on the work of Petrov at Kazan University. And then the fundamental work of the description of three massive particles moving in the Kerr metric, which was done by Carter, myself, and Wheeler, and are quoted in Landau-Lifshitz with all the effective potential and what later on became known as the ISCO and so forth, which are contained in this Landau-Lifshitz volume. And then the mass energy formula of the Kerr metric discovered by Christodoulou in 1971, soon later extended by Christodoulou and myself, and Stephen Hawking to the case of the Kerr-Newman. Here I show the remarkable day in which Dimitris Christodoulou, who had arrived from Greece at 16, discussed his thesis in Princeton. The person who really listened and made the most profound discussion was Eugene Wegener, while myself and Wheeler were listening as a reference of the thesis, and also other professors were present, questioning and asking questions. In those period, there was an article which we did with Wheeler, introducing the black hole. And this article went all around the world. The name black hole was translated in practically all languages. And the starting point of this research happened with the mass formula of the black hole, which was obtained by Christodoulou for the Schwarzschild and Kerr case, extended to the Kerr-Newman solution, and practically on March 1st, 1971, and at a distance of 10 days by Stephen Hawking. This is a beautiful picture that we had not at the time, but in 2017 in Cambridge. One of the last time I met with Stephen to celebrate our formula in presence of Roy Kerr, which is present in this picture with his wife. These were the beginning. But let's go back to gamma ray burst. A fundamental discovery happened due to the Vela satellite in 1972. And it was after this satellite of Vela which the Gamma Ray Observatory was launched with BATS and IGRET, and the first data, not just a few days after of the discovery of 1972, but quite late, after 20 years, was the understanding that the GRB were possibly to be generated by a black hole in the work of Rees and Metzaros, and in the work summarized by Metzaros and Piran. These were the glory day in which the discovery was first presented in San Francisco in 1972 in this beautiful, simple book by Gursky and myself, which I will return later on in the presentation. The first gamma-ray data from Batze showed isotropy in space, but the real great revolution, the new era of gamma-ray burst, was started by the Italian-Dutch telescope Beppo-Sachs, which associated in a single mission both the expertise of the X-ray astronomer and the gamma-ray astronomer, which had been dominating the field of GRB since the Vilo satellite, the CGRO. From this mixture of the X-ray and the gamma-ray community, it came the miracle, the improved GRB position, which before it was impossible only on the gamma-ray data to identify the source, but due to the very narrow position due to the X-ray afterglow, a new fundamental discovery was made. The first determination that the GRB were really cosmological from the measure of their distance using the cosmological redshift of the associated galaxy by Metzger et al., and the consequent determination of their energetic, which was of the order of 10 to the 54 ergs. What means 10 to the 54 ergs? One of this GRB coming at distance of 10 billion light years away and appearing on the Earth like a nuclear bomb explosion in the Vila satellite had really an energy of the sum. If you take all the stars in the galaxy, they are of the order of 10 to the 12, each star with an energy roughly of 10 to the 33, which gives an energy 10 to the 12 times 10 to the 33 gives 10 to the 45. And this we are still a factor 10 to the 9 smaller than the GRB, because the 10 to the 9 is equivalent to the number of galaxies all over the universe in our past light cone. Therefore, the GRB, when it explodes, at the energy of all the stars in the universe for the time it is shining in the sky. And therefore, one of the next incredible and very, 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 very important observation, in addition to the one which I just mentioned, starting from the Vila satellite to the GRO, to the Beppo-Sachs determining the X-ray and the position, and then transferring the data to the largest optical telescope in the world, and was very lucky that in a certain sense the Uhuru satellite, the satellite from following Uhuru from Beppo-Sachs was a little late, in a sense that it was just in time to the develop of the Keck satellite, the Keck observatory, and later on the very large optical telescope in Chile, to make the optical observation of these stars and their identification of their distance due to the redshift possible. But the greatest discovery after Beppo-Sachs was an observation due to the new European telescope in La Silla, in ESO. And there, again, for the first time, a GRB was detected together with an optical supernova. And this was the starting point of all our research. What is the role of supernova, which is much weaker in intensity and luminosity than the X-ray? What is the relation between these two? And this is the topic on which our group in ICRA and ICRANET has given the contribution in the last 25 years. For explaining this relation of the correlation between a supernova and a gamma ray burst, a new concept was introduced starting from the induced gravitational collapse by Rueda and myself, which and involved the collaboration with Los Alamos National Laboratory and the group of Chris Fryer. This binary model, or the binary-driven hypernova, assumes as a progenitor a binary system composed of a CO core and a binary neutron star companion. And there are three different kinds of BDHM type exist, mainly as a function of their binary period. The collapse of the CO core leads to the supernova explosion with the creation of a new neutron star which originates the X-ray afterglow. Well, after so many years of work, after 25 years of work, the result of our model relating the GRB to the supernova has finally been completed since the 1st of October of this year, when the publication of our group appeared in APJ. Of course, there are some 200 references of previous work, but now everybody can see the final conclusion. I will just give a few examples of this paper and summarize on this paper. I first will look at the binary system of a supernova done by Laura Becerra in collaboration with Chris Fryer and Los Alamos, in which you have Yes, we are fixing. Oh, ok, ok. Ok? Posso andare? Posso andare? La registrazione? Condividi? Sì. Ok, possiamo ricominciare di qua? Ok, please confirm that you are listening. Okay, the great following this initial period and the Beppo Sachs, a big effort was involved in the creation of VLT, of many satellites, the Niels Gerels, the Fermi Gamma Ray, a major astrophysics magic discovery, and was in this using all this information that we built the model of type to study the supernova which are related to the binary driven hypernova of type 1 or type 2 and type 3. And we look at the observation of 24 spectroscopically well-identified supernova associated with long GRB supernova. And in table 1, we give the name of the supernova type, the cosmological redshift, our best estimate of the E-ISO of the associated long GRB, the peak luminosity of the supernova, and the time of occurrence of the peak. We also give the analogous information from the literature in the following 3 slides. I don't like, well, you will see this in the paper, the detail, but the key point of all these 24 supernova, which has been very surprising, is that their luminosity, independently of the redshift, which of course for the observation has to reach the maximum value of 1, but is independent, the luminosity. When you go in the local rest frame, the luminosity is practically constant. The trick is to go in the local reference frame, correcting for the Z, and also the time in which the supernova occurs is of the order of 10 to the 6 second, of the order of 2 weeks. But what was more, in addition to this fact that we had only 24 of them, but it looks like this supernova related to GRB, not all the supernova, but the one related to GRB, the type 1b and 1c, have a standard luminosity. And if we keep going to L to Z larger than 1 with the available telescope today, the James Webb, in principle up to Z equal 3, we could fill in for many more supernova. Of course, with the data of the Vera Rubin telescope, this number can increase very much, and we could check if indeed this supernova can give a standard candle. But the interest for us is not only the constancy of this supernova, but also the fact that there are 3 types of BDHN, one between 10 to the 47 and 10 to the 50, one between 10 to the 50 and 10 to the 52, one between 10 to the 52, BDHN 1, BDHN 3, which fits, which are related to this in a very big range of energy, related to a standard supernova. And I will give you, I cannot go too much details, but I will give you just some example of GRB of type 3 example of type 1, type 2, and type 3. And they are all these GRB are characterized by 7 episodes, and together with the standard IC supernova. And the VDHN1 are the most energetic class of long GRB, with energy between 10 to the 52 and 10 to the 54. The characteristic, their orbital period is of the order of 5 minutes, the orbital period of the companion neutron star with the CO core, which implies a separation in the binary of 10 to the 10 centimeter, just close to the CO core star, CO core radii. The hypercritical accretion of the supernova ejecta onto the companion neutron star leads to reach the critical mass and consequently form a black hole. This energy of VDHN1, which is larger than 10 to the 52 erg, is explained by the synchrotron radiation emitted by the new neutron star in the X-ray, optical, and radio, as well as the radiation in the MEV in the UP phase and in the JEV radiation originating from the rotational energy of the newly formed black hole. Well, this is one, I cannot go too much in detail, but I can just give you a few examples of the different physical process, 7 different processes occurring in the evolution of a binary-driven hypernova. We start with the collapse of the CO core, which is the episode 0. Then, as we have seen in the picture, you have the formation of the new neutron star just where the gravitational collapse happened. And this we observe with the corresponding spectrum. Then we have a second phenomena, a second episode, where the accretion of the matter into the rotating newly formed black hole give origin to an overcritical field which generate electron-positron pair, and we have all the details of the spectral properties of this electron-positron pair with baryon, creating the emission of this UP phase here, very close to the beginning. And then we have again the appearance of the new neutron star and this different process. But by far, one of the new physics which we have unveiled is the fact that the electron-positron pair in this UP phase is overcritical. And if you take this data, which last only of the order of 2 seconds, and you divide this data in two 1 second period, you see that the spectral property is the same. And then if you go and divide still by 2, you have again the same spectral structure, and again going on and on and on, until there are enough photons to have a statistic, you have this self-similarity and fractal structure. And this has been a completely new physics which we have discovered in the GRB and we have seen all over. Therefore, there are different phases, which you will see in the paper, 7 different episodes, going from the generation of the overcritical field to the critical field generating the JEV radiation to the synchrotron radiation emitted in the afterglow. In the case of the BDHN 2, the accretion of the supernova into the companion neutron star does not reach the critical mass. And therefore, what we are led to is a system less energetic than the BDHN1, and the characteristic energy is between 10 to the 50 and 10 to the 52. And that explains why the absence of the critical mass accretion explain why this system are not forming a black hole. Therefore, you don't see the JEV radiation, but you see a weaker emission, and you see the afterglow regularly. This is a classical example of this type 2 supernova. And again, if the binary period is larger of the order of months between the orbital period, which is the key, of few hours, in this case, the separation between the CO core and the neutron star binary is 10 to the 11 centimeter. The energy is weaker, and the new neutron star reach period of 50, between 50 and millisecond, which are sufficient to explain the afterglow. We reach the complete understanding of these systems. And this is very, very beautiful. And there are all these 7 episodes, which is completely new physics, going from synchrotron radiation in the X-ray, optical, in radio, going to the JEV emission into when the black hole is formed, and there are all the physics of this effective charge distribution of the black hole, the inner engine. We have developed all this in many, many tens of papers. And the key conclusion are that only IC supernova associated with GRB have the same luminosity. The standard CO core is approximately 10 solar mass, collapsing. The crucial parameter is the initial period of the binary composed by the CO core and the companion neutron star. This era of cosmic energy sources has started. There are practically 3 eras: the cosmological nucleosynthesis done by Fermi and the cosmic microwave background, which has characterized the early phases of the energy source in cosmic sources. Then there has been a second period from stellar nucleosynthesis, started with Bethe, Barbish, Fowler, all the way to the Boraxino experiment, which have characterized the evolution of stars. But now we are speaking about the third era, a quantum electrodynamical energy extraction process from rotating black holes and neutron stars, which are based on the Christodoulou and myself formula and Dawkins, and by the Kerr emission. But I would like to go back to my promise. What can, okay, you can see all the details in our paper, but what can we learn from BDHN for Cygnus X1? This is the topic I promised in the last meeting in Mexico City, in Colegio Nacional. Okay. This last paper is dedicated to the fascinating story of Cygnus X1. Let's go historically. One of the key contributions that I made to the field of black holes has been to understand out of first principle that just on the ground of general relativity, very general principle of Letellier and the fact that there is a fiducial density under which we can estimate, maximize the mass of a neutron star, and extrapolate to higher regime with limit due to causality, is possible to establish an absolute upper limit to a maximum mass of a neutron star in 3.2 solar masses. This result is in Fizerev letters and has a lot of citation. And I think has been the first motivation to identify a black hole. It was already in 1973 which I proposed the identification of Cygnus X1 based exactly on that theorem, that there is an absolute upper limit on the mass of the neutron star. Therefore, the fact that in Cygnus X1 you have an energy of 10 to the 4 solar luminosity in the X-ray could be expressed both by accretion onto a neutron star or a black hole. But the fact that there is absence of pulsation, of regular pulsation, was simply explained by the uniqueness of the Kerr-Newman metric, which is actually symmetric. And then the key factor was that the mass of this system was larger than 3.2 solar masses and therefore had to be a black hole. We had a fantastic meeting of the 6th Texas meeting in New York in December 1972. There, in a session very, very exciting, which was chaired by John Wheeler, I proposed the identification of Cygnus X1 in a black hole, and soon after, in December 1972, I got the Cressy Morrison Award for this proposal by the New York Academy of Science. But let's go back a moment to Cygnus X1. Well, Cygnus X1 was discovered after a certain flights by balloon by Tannenbaum and Otter. But the key information was obtained by Oda, who was working at the time at American Science Engineering, and this is the famous paper in which Oda, with Gorenstein, Gursky, Schreier, Tannenbaum, Kellogg, and Riccardo Giacconi, identify and observed the structure of Cygnus X1. And that, I insist on this, because I take this from my book with Gursky. What Gursky emphasized is that from this first data of Cygnus X1, it was clearly that there was no regularity, but they were down a few milliseconds data with a lot of structure flaring down to a fraction of a millisecond. This was the characteristic of the Cygnus X1, the high variability on very short time scale. And this was obtained and observed by Oda and by Gursky. And this is a picture where you show how the average value, extended averaging over a long time second, the system becomes just flat, but it's on the short scale, and I will come back to this, on the short scale, that there is the uniqueness of Cygnus X1. Let's go back to history. Cygnus X1 has this flaring activity, which is the high state, But originally, when it was discovered, Cygnus X1, the figure on the first up figure on the left, was at a minimum in a low state. And I insist the difference between the high state and the low state has not yet been understood. And very likely we have now data which are very relevant, which I will present later in this presentation on this topic. But what was very important in the transition, which we have to look very carefully, between the low state and the high state, is that an X-ray, an optical source appeared, and the optical source, thanks to Gelming, allowed the position of Cygnus X1 much more accurate. And here you see the data from the radio on the right side, which localize uniquely the Cygnus X1 much better than the X-ray position of Uhuru. And that allowed the identification of the companion star, that Cygnus X1 was indeed a binary. And the binary period was established between a large mass companion star accreting into Cygnus X1. These were a dramatic moment which we all shared, and they are remembered in the book which we published with Herb Gursky. And after that, the first data appear. Brucato and Christian gave a range between, you can read, between 5.5 and 22 mass for the companion. Hutching gave a large value of the black hole mass. Sunyaev gave up to 17 solar masses, and Bolton up to 20. But what is the very important data, which I summarize again in my book with Gursky, is the data of Rothschild, which he gave the structure up to a few milliseconds in the flaring. The X-ray data of Cygnus X1 are flaring on very short time scale. And if you put the value of the black hole of a few solar masses, and here you see and A equal m, you can indeed agree with the flaring should happen of order of a fraction of a millisecond. This is what we learned. We knew already back in the classical data which we had acquired before. Of course, Ricardo was very happy about, and later on was the jubilee of following his Nobel Prize, which we all were very happy, and he could recall our previous work. But let's go back now to the real problem of Cygnus X1. What we really understand is that Cygnus X1 is different, definitely different from the GRB object. The GRB objects are of the order of 10 solar masses, and there was a paper which I consider marvelous. Of course, we did not give a proof, but was the first idea that indeed if you have very big masses star of the order between 100 and between 10 and 50 solar masses, what it can happen is that only a progenitor star up to 20 solar mass can generate supernova. And then the idea was presented by Fryer that indeed, if you have more than 20 solar masses, you could have a fallback and forming a black hole. Or otherwise, if you have even bigger mass, you can form directly a black hole. This was a pioneering, beautiful work, which is still a pleasure to read today. Another paper which was extremely influential and important was this paper by Smart. I have not the time to go into the details, but in this work, Smart painfully and diligently studied all the stars which generated supernova, observed supernova. And he found out that the progenitor of all supernova known has been necessarily below of 18 solar masses. This added very much to the conjecture of Fryer, and even more, there was a third component due again to Fryer, especially Woolsey and Hartmann and Langer, of course, and Heger, that indeed, if you have a star very massive, you could have a direct collapse to a black hole. Therefore, it became very clear this was not a proof, but was definitely a possibility that while in binary X-ray sources, you form black hole by accretion on a neutron star, and the black hole are of the order of 6, 7 solar masses. And of course, you can create a lot of such system. We know now many, okay? But all these black holes are completely different from Cygnus X1. And let's go to the fact. What is very exciting today is that a big effort has been done thanks to the data of Gaia, thanks to the data of VLBA, and by the group led by Miller-Jones at ICRA in, not ICRA, ICRAR in Australia, and the new mass of the black hole with great accuracy has been established around 21 solar masses, larger than the value which was conceived before, but of the same order of magnitude. And it's very, very important to clarify better data from the very large by Gaia, this beautiful work done by them, is necessary to keep going on in determining better and better the data of Cygnus X1. Now, there is another set of work on Cygnus X1. This second work has been to determine from the work by the Chinese group led by many the possibility that the Kerr black hole originating Cygnus X1 has A over M very close to unity. This work was, in a certain sense, motivated by a strange work by Novikov and Thorne, which I refer in still present. Hello? Hello? Is that okay? I am concluding. And by Thorne but that was a very critical work because it was the work of Rashid Shumyayev and his co-workers that was given to Novikov to bring to the meeting in Les Ouches, and then transforming this paper, which was not really referred, but I don't want to enter into this point. But let's go to the next the next discovery, which is really very important. The imaging X-ray polarimeter, which was invented by Enrico Costa and his team. Enrico was the same one who invented worked for the first time on Beppo Sachs and the identification of cosmological GRB. But this beautiful instrument, what has been able to do is to give the first evidence that there is polarized X-ray emission from Cygnus X1. This is a fantastic result because for the first time we see the jetted emission from Cygnus X1. And we see also the angle with respect to the viewing angle. And they are all the details in this fantastic paper. Therefore, the conclusion that we have to do is that Cygnus X1 is alive. Is alive, is not a dead black hole, but is a black hole which is generating the electrodynamical properties due to the Kerr-Newman solution. The jetted emission of the observed by IXPE is the revolution on the observation of Cygnus X1, which may well lead to the understanding of the millisecond temporal radiation in the observed flux on the I state of the quantum and classical overcritical electrodynamical and general relativistic effects, which are observed in the UP phase of GRB. This is the complementarity between GRB, the very overcritical field, and the physics of Cygnus X1. It is also essential to identify and follow the observation with IXP of Cygnus X1 in order to verify the possible turn-off of the jetted emission and consequent understanding the underlying physical process. This observation opened the gate of approaching a new understanding of the physics of the extreme Kerr-Newman black holes, which we are currently under scrutiny. Therefore, this is a new era. Cygnus X1 is alive and is through the complementarity between gamma ray burst and this fantastic observation by IXP, which we can progress in a new era on general relativity, quantum and classical effects, and also on the uniqueness of the Kerr-Newman black holes. Thank you very much. And with that, everything has been made possible thanks to the work of Albert Einstein, and especially also with the work incredibly verified at every level of Roy Kerr. That's it. Did you follow?
Are there any questions?
Thank you. Thank you very much for a very interesting talk. My question is, so this detection of the jets from Cygnus XY, so how constantly these jets can be observed from this Cygnus XY, one black hole? So they are constants, or what? How frequently these jets can be observed?
Okay, this is the key point which I showed in the first, which you can find in my paper with Gursky. I think the most exciting result is the fact that you have initially a low state and then turn on in a high state. The high state is the one which follow the very, very fast variability presented by Gursky and presented in the ODA data. But then you have the jetted emission, and there are periods in which the jetted emission is there are variability on different time scale, and the short time variability disappear. My guess is that we have to follow this transition, which happens every few months, and for the first time to look back immediately, as soon the low state starts, to look back immediately with IXPE to show if indeed the jet has disappeared. And this is very fundamental, because this has to essential for identifying the nature of the jetted emission by the electrodynamical process. Therefore, the observation of low state is now urgent in order to verify that when you have a low state, the jetted emission has disappeared, and therefore we can understand much better the condition under which this happens. There are many different possibilities, many, and one of the most exciting one, if I have to mention one, but has to do with the Kerr-Newman uniqueness also, is that if A over M tends to 1, there could be a Meissner effect occurring, which throws away the magnetic field. But this is just one of the possibilities. There are many other possibilities, but the point is now the time to study Kerr-Newman black holes together with the information of the UPE from the vacuum polarization in GRB is essential. It's a new era starting. Therefore, I thank you for giving me this opportunity to stress these unique properties of Cygnus X1. But again, when we met in Les Houches, I insisted that there are black holes dead and black holes alive. What I meant is black holes which dead are the one like the Schwarzschild black hole without energy extraction, and then there are the alive one which have jets, which are accreting like in the GRB, accreting and therefore being active and seeing the extraction of rotational energy of the Kerr black hole. Cygnus X1 is alive. This is extremely historical point. Up to now, there was no evidence for that we could have thought that Cygnus X1 was just a dead black hole. No, it's alive, there is a jet, and we have to have the great opportunity to understand the interface between general relativity, quantum, and classical over critical field, which has become very important today. We are just working with Eli on the possibility of simulating this electrodynamical process with plasma, ultra-relativistic with laser, and this is the real future of this field.
Okay, thank you. But just the last remark, because if these jets are emitted regularly, I think this is very important because one of the explanations for the jets which existed earlier, that these are due to the gravitational collapse of non-equatorially symmetric objects, so is not valid. So I think that your theory is preferable. Thank you.
Well, we are now we have the first example thanks to IXPE observation of the jet. Now we have to encourage them. They have a great team in US, in Italy, in China, even all over, working on this system. And I will speak next lecture in Hong Kong about another possibility due to the IXP observation of the remnant of the crab, that very likely there is a black hole in that remnant, and therefore that we are speaking about something very revolutionary, that very likely the supernova of 1054 was really a GRB. But this is something new which is coming out from this fantastic small telescope of polarimetry, which directs not only at Cygnus X1, but also to the remnant of the crab. It's a completely new era. I would like to stress how fantastic is this new era. I will speak in Hong Kong in a few weeks' time on this topic. But it's a new era.
Any other question?
Yes, a comment? Thank you very much for your story, Professor Ruffini. I see that you combine all the X-rays and all the high energy observations, but the optical observations, since the very beginning, knew the exact position of the source of Cygnus X1, and also knew that it had a companion that was indeed very massive. And it had a name, actually. It had HD 226868, which was already, cataloged and well known for its position. And the observations of Tom Bolton from Canada suggested that it had a companion that was unseen, and they had a huge coincidence with this X-ray source.
Yes, I just show you from my book with Gursky this figure which refers exactly to the data of Bolton and the determination of the companion neutron star, or the companion main star, which is, as you mentioned, HDE 226868. But what I wanted to emphasize is that this identification was made thanks to the very interesting transition between the low state and the high state of Cygnus X1. As soon as this transition occurred, here on the left, the radio source appeared, and the position of the radio source unambiguously identified the source of Bolton. And this was really the fantastic coincidence. This is the reason why I insist on this history. And as soon as this happens, of course, the work of Bolton became crucial and extremely important, and we give this, you can see in this book of Herb Gursky and myself, which was done at the time in which this field was just starting. Thank you for mentioning this reference to Bolton. But indeed, the key point was not only to look at the star, but to find the identification to the radio observation. And this is the reason why we would like, I think we have to understand better the turn off and on between the low state and the high state. I think IXP should continue and give us the opportunity to see a transition back from the high state to the low state, and therefore to the absence of radio emission, but to understand the physics of the quiet state. I think this can be very important. Compare and contrast. If this happens by some general relativistic effect like Meissner effect or other, but this is all new story to be looked for, beautiful story.
Raymond, thank you very much for your very interesting lecture.
And I would like to say hello to everybody there. And especially, I have heard that Pablo Laguna is there, my old friend. I hope to be soon to continue this presentation at this beautiful university in Austin, Texas. And we want to celebrate this, a great friend who received the Marcel Grossman Award, and bring there the statue to Steven Weinberg Memorial in the Steven Weinberg Institute that they are building there. A great future and a great possibility to continue the flag flying of general relativity, fundamental science, and big discovery, which are now becoming really much more exciting than just a few weeks ago. And please don't forget to read our paper of 1st October of this year.
Okay, bye-bye.
Thank you again to give me the opportunity. I have to thank this professor from the mountains who asked me the question at the last meeting, but how you explain Cygnus X1? At the time, I could not answer. I was struck by the beauty of the question, and I have been working since. But we have been able to give the answer only this week, and I rush through to give this presentation thanks to your very kind possibility to use the electronic means. Thank you again.
Okay, let's have a break, a coffee break, and we will continue after the lectures of Professor Rafidi at 11:45.
I will try to have a
the
to send to you.
Symposium.
Thank you again, Marcia. Alfredo, are you hearing me? Alfredo? Massimo, hai seguito? Massimo? Hai seguito?
Sì, ho seguito tutto.
Hai capito?
Beh, penso di sì.
È